So thank you for the introduction and for the invitation. And these works are joined with Daniel Gerbner, Balázs Keszegh, Dömötör Palvolgyi, Balázs Patkos and Gábor Wiener. So I would like to show you a brief introduction to a variant of a search problem, which is called majority problem. So what is the problem? I would like to define first that. Suppose we've got a set of n indexed balls, and they are colored with some colors, but a way unknown to us, and we want to find a ball possessing some kind of property by asking some questions. So it's a very general framework. I want to specify first this. So let me define what is a majority ball. A majority ball is such that its color class is strictly larger than n half. So and the plurality ball is one such that its color class is strictly larger than any other color class. We want to find these balls, a majority ball or a plurality ball, by asking some questions, and this will be the majority problem. So the aim is decide whether there exists a majority or plurality ball, and show one, so the index of that ball if there exists. And so it's easy. It's just a remark. If the number of colors is 2, then this problem coincides. Okay. Actually, I will show you some motivation from some practical point of view. There is a fault diagnosis model presented by these three guys, Preparata, Metze, and Chien. And they wanted to find, so suppose we've got processors and we want to locate the faulty ones, and I won't show you the exact algorithm, but they presented an algorithm how to find it, and they point out that to be able to find the faulty processors so there is a necessary condition. A strict majority of the processors should be fault-free. So if we want to use their algorithm, first we want to test whether the strict majority of the processors is fault-free or not. Okay, so it's just a motivation why, for example, we want to investigate these problems. Okay, so back to the problem, to the majority or plurality ball problem, and we've got two main sort of algorithm. One is the adaptive version, when the answers and the queries, so the query is the question, what we will ask. We asked a question and we've got an answer. Then again we ask a question, we have the answer, and so on. And in the non-adaptive version, we should ask all the queries first. Okay, so note that a non-adaptive strategy is also, you can look at it as an adaptive strategy, asking the queries independent of the answers. And therefore, the best non-adaptive strategy always uses at least as many queries as the best adaptive strategy.
But what is the query? What type of queries?
Okay, I will specify in different models the queries. Okay, so first look at, for example, the pairing model is the most basic model. So again, we've got the n indexed balls, each of them colored with some colors, and we ask a pair of balls, and the answer will be that they have the same color or not. And the goal is to decide where there is a majority ball and show one if it exists. Okay? So this is the very basic pairing model. Okay, and Fischer and Salzberg in '82 proved that if the number of possible colors is unknown, then the minimum number of queries in an adaptive search for a majority ball in the previous model is roughly 3n over 2.
But this assumes that we need to give a definite negative answer. We are not allowed to give some ball which is a majority if majority exists, because otherwise the n is enough. Definitely.
Yeah. So if there is no majority ball, we have to say that there is no majority ball, and if there exists a majority ball, we have to point the index of that majority ball. Okay. So, but if the number of colors is 2, then in the adaptive model, Sachs and Verban precisely answered that how many questions do you need. So the number of the questions in an optimal strategy in this model is n minus bn, where bn is the number of ones in the dyadic form of n. Okay. Okay, so it was the pairing model, the majority problem, and in the adaptive setting. Okay, then look at this model when it's non-adaptive. For this model, Eigner proved in 2004 then if the number of colors is 2, then the number of queries in a non-adaptive search, also in the pairing model, is n minus 2 if n is odd, and n minus 1 if n is even. So it's the majority problem, but the non-adaptive problem also for the pairing model. Okay, and let's look at the plurality. So now we are also the pairing model, but the plurality question and the non-adaptive version. And let's denote P and C, the minimum number of queries needed in a non-adaptive search when we have n balls and C colors. And Gerbner, Katona, Palvolgyi, and Patkos in 2013 improved earlier results of Changrehev, Mao, and Yao. And actually they as you could see, they proved these inequalities. They gave a lower bound and an upper bound. So they could prove the order of this P and C. So it's quadratic. So they proved this result, and this is the best result still then. And there is no, in the literature, there is no result for the pairing model and the plurality plus adaptive. So there is no known result for that. Okay, then let's generalize this pairing model. Also, I'm talking about what is in the history. So how can you generalize it? So, for example, the first generalized pairing model is the yes-no model. Now the query is a case set of balls, but the answer is that they have the same color or not. This will be the answer. You can easily see that if we ask a 2 set, then it is the pairing model. Okay, and so this is the yes-no model. And if we use this notation, this Q sub K, yes, no, n, for the minimum number of queries in the adaptive version, then DeMarco and Kranakis proved this result last year. for this model. So they could exactly give the answer if n is 2k minus 1, and they could prove a lower and an upper bound for the minimum number of queries you always need this upper bound. So here is an n over k, and the upper bound is n minus k plus. So there is a gap between them. Okay, and there is another generalization of the pairing model, which is we can call it a pairing model or a k-pairing model when the query is a k-set of balls, and the answer is they have the same color or a pair with different colors. In the yes-no model, we just said that they have the same color or not. Now we have to point a pair with different colors if they have not all the same colors. So, and also the goal is there majority ball or show one if there exists. Okay, DeMarco, Kranakis and Wiener proved in 2012 that if n is at least 3 and we ask 3 queries, so we ask 3 sets, then they could prove that the minimum number of queries in this version you need is roughly n over 2. And 2 years ago, Borzyskovsky could prove an exact result for if you ask k queries. So he could prove these results. Okay, so again, I do not know any result. So I talked about the yes-no model here, and now I talked about the pairing model, and I do not know any result about the plurality and the non-adaptive versions. Okay. And there are other models also introduced by DeMarco and Kranakis. For example, if the output model, when the answer is a partition of balls such that I is the balls of one color and I prime is the other, and also the counting model. I just mentioned these models because I want to show you that there are many generalization of the basic pairing model if you use k-sets. Okay, and Epstein and Hirschberg just in this December uploaded a paper to archive when they proved these results. Then almost yes.
These are adaptive, right?
Yes, these are adaptive versions. Thank you. Okay, and okay, I just mentioned that these results are just 3 months old results. Okay, and now I want to introduce our model. So we want to generalize also the pairing model in another way. We will ask k queries, but in this first model, I will show you for 3 set queries. So and the answer will be the index of a majority ball in that 3 set. Okay, so again from the beginning we have a set of n index balls, each colored with 2 colors in some way unknown to us, and we can ask 3 set of balls, and the answer will be the index of a majority ball, and that will be our model what we will investigate. Okay, but this first model is not so good because even asking all triples, we cannot guarantee that we can solve this majority problem. And here is the counterexample. If we have an even number of balls and they are partitioned into two sets of the same size, and the answer for any triple is a ball from that x if the t intersection with x, the coordinate of t intersection of and x is at least 2, then we answer a ball from x and otherwise from y. Then in this case we cannot decide whether all balls have the same colors or all balls in x is red and all balls from y are blue. Okay, so we wanna modify a bit this model, and for this I wanna introduce a new notion, which is the non-minority ball, is such that its color class has a size at least n over 2. So not more, but at least. So note that if n is odd, then the majority balls and the non-minority balls are the same. Okay. And our model will be the following. So that's the model. We ask Q sets, and the answer is the index of a majority ball in this Q set, or we say that there is no majority ball in that Q set. Okay, and we want to find a non-minority ball. Okay, and I will show you results for this model. Okay, and this model seems a bit artificial. However, it is the same as a bit more natural model. It is the same as finding a median element from an n-element set of zeros and ones. So now I want to show you that our model is the same as the following model. Suppose we've got n element, zeros and ones, and we want to find the median element of that zeros and ones. And we can ask queries of size q. And the answer is whether in that Q element set the median is a 0 or a 1. And we've got this result that for the adaptive, so in our model, if we ask 2l plus 1 elements, is the same as asking, so the length of that the length of finding the majority or the non-minority element in our model is the same as finding the median element in this model, and also for the non-adaptive version is the same. Okay, and our result is the following. If you ask triple sets, then you can find a non-minority element in linearly many steps. And to find the non-minority ball in the non-adaptive version, asking by triples, you need cubic many questions. Okay. So that's our main result. And I want to just sketch briefly the proof of this result. So first of all, we want to find, with asking these triples, two different balls in linear time. How do we do this? We start with an arbitrary query, and we just remove the majority ball. Then put another ball instead of that majority ball. Then again ask this triples set, this triple, and again ask the and again remove the majority from this triple. And we repeat this procedure for n-2 times. And at the end, we will have two balls. If these balls Bi and Bj are of the same color, then it's easy to see that all the balls have the same color. You can just think it over easily. And so we can suppose that they are of different color. And the next slide, it's an easy observation. It's a bit technical, this statement, but it just says that if we've got two different balls, then we can define an order on the balls. So actually, instead of colors, this slide is just saying that instead of colors, we can talk about zeros and ones. It's just this. The meaning of this observation is just that. So remember from the previous slide, we've got two different colors in linear time. Now, with this observation, we can talk about zeros and ones. And now the main thing that we could modify the median of medians algorithm of Bloom, Floyd, Pratt, Rivest, and Tarian. That if we've got an n-element multiset containing zeros and ones, such that we know that x1 is 0 and x2 is 1, and we can ask queries, and where the answer is either that A is less than or equal than B, or B is less than or equal than A, or A is not equal to B. So this comes from the previous observation. Then we can find the k's largest element in linear time. So that's the heart of the proof, that we could modify this median of median algorithm to find the k's largest element in linear time. Okay, and actually that's the proof of this result. Then in the adaptive search, asking by triples, we can find a non-minority ball in linear time. Okay, and actually we had some results for larger query sets. You know, you can see that there is some difference if you ask queries of even size or odd size. For example, in the non-adaptive search, if you ask queries of odd size, then you need at least cubic many questions. Whether if you ask queries of even size, then you need at most quadratic many. So that's an interesting phenomenon, that there is a difference between the even size and the odd size in this model. Okay, so for the last slide, So there are many questions in this topic. For example, the plurality case wasn't really investigated even in the basic pairing model. And for the other models, for the other generalized models, for example, the non-adaptive versions weren't really investigated. So many questions. But as a first question, I put here that the A sub 2L plus 1 is just linear. Is it a question?
Can you say again what is AA to this A?
AL, yes, this adaptive. You ask adaptive K plus 1s, and the answer is whether there is a majority. So if there is a majority, and if there is one in this K plus 1, they show 1.
But even if you compare two of them, in the basic model, it seems that, for example, if there are two coinciding and all others are different, there is no chance to find this coinciding pair before looking at all pairs, essentially.
But this 2L plus 1, it's not a pair. You ask just, for example, 5 sets, or 7 sets, or 3 sets, or...
You have only 2 colors.
And only 2 colors?
Only 2 colors, sorry. Yeah. So you've got 2 colors. You ask the 5 sets, for example, and it is a question whether you can find a non-minority if they show you a majority in that 5 set. And you can do whether you can do it in linearly many steps.
And you have n with 3 over 2, right?
Yes. Sorry. Yes. Yes. Up to a log factor. Polylog factor. Yes.
Okay, so maybe you can somehow advertise the field in general. So maybe some simple, nice but non-trivial argument, either positive or negative, to show that there is something exciting here. What is the most exciting simple thing in this theory?
Simple thing.
Yeah, but exciting. No, there is one real thing, the original thing. If you want to compare the pairs and you want to find the majority,
Yes.
you are guaranteed to have a majority. Then you can just have a very nice algorithm to find one of the majority elements in linear time and in 3 lines and so on. But something else, more advanced but still exciting and simple. Is there something, some lower bound, or maybe it's because maybe it's on the other type of advertisement. Maybe it's somehow related to some other fields, and you can get a lower bound for something else by reduction, or so. Just why should we care about this? Just
This majority.
Question.
Yeah.
So I think I'm one of the co-authors. So I think the most exciting is definitely
Not in this work, just in the field.
In the field is this n minus bn exact result for the 2 colors, 2 queries, where bn is the number of ones in the binary representation of n. I mean, that's just on its own. How cool is that? That comes up as an answer.
Okay, but then can you just prove it now, just to show it's cool?
Well, you want the upper one or the lower one?
Whatever is cooler. Just something simple, but not extremely trivial. Okay, but just something simple and nice from this big. What is the take-home message? So we came here and we remember that there was a nice argument for this. So
Okay, so do you know the proof for that?
For the upper bound, I mean, okay, so basically, what can you do? I mean, the trivial algorithm which would give n minus 1 is just to just to, as a graph, make it connected. So ask two sets to make a connected graph, and then you know everything. Because you know that, okay, so if this ball is red, then this one is its neighbors, you know if it's red or blue, and so on. So if it's connected, you know the two color classes. Okay,
Yeah.
and it isn't really how to improve that. What else can you do? Of course, if there are multiple components in the graph at the end, the resulting graph,
Yeah.
then the only thing that can help is if some of the components
It's
have
big and it's
discrepancy,
uniform.
have discrepancy 0, or so that the two color classes have the same size, because then you can forget about that component. But if you have two components with different, which are unbalanced,
Yeah.
so then you cannot find the majority ball. So how can you force that you have several balanced components? Well, the thing is that you ask a query. If the answer is that they are different color, then you are happy and done. If not, then it means
So if you see that the two things are different, you can just delete them completely.
yes, and
It
then
doesn't
you are
change the majority, yeah.
Yeah. So the answer most probably will be that they are of the same color. Then you ask another two, that again of the same color. So you get two small components. That
So
are
you have a
very
big component
unbalanced.
of the same color and some discarded pairs. That's what you are saying, yeah?
Well, I mean, in general, so the adversary won't want to help you by discarding pairs, so he will never do that. But how can you force him to do that? So you have these two color classes after the two components, the two pairs after the first question that are.
But I'm sorry, just if the adversary doesn't help us by discarding pairs, then we get bigger and bigger connected component. And if it
bigger
achieves n over 2,
Yes.
we are done. So it's
Yes,
not the,
yes,
for adversary,
yes.
it's not the best strategy.
Well, the best strategy for the adversary is kind of to make sure that it happens as late as possible and as rarely as possible. So he will wait till the color classes would get over and happen, only then will allow us to discard them. So what happens is
Yeah.
basically that when you discard the color class, that has some size 2 to the I, or some I. So that's a power 2. And in general, that's going to happen that you discard with some color classes that have a size which is the power of 2. At the end, you will have components, so you will discard color classes, discarded the components. At the end, when are you done? When the remaining components, you know that they are all monochromatic, all powers of 2. If they are all different powers, then you are done, because the largest power dominates all the smaller ones, so that's when you are done. So basically you wrote an endless sum of powers of 2, and this means that the numbers, these powers of 2, have to be at least Bn. Because Bn,
So somehow you say that this Bn is related to the question, to the number of, so the situation when for every, you split n into powers of 2, and they are uniform, while you know nothing about the interconnection between these components or something like this.
well, there isn't interconnection between the components, really. But so basically, so that's the.
How B of n appears? Just the
So just-
units
just
in
that-
n correspond to
just that-
component of size exponent
just that,
2 to the k, yeah?
Well, so at the end, n is equal to the sum of two powers, and what you what you want is what you gain is the number of components. So if you ask all the questions to make everything connected, n minus 1 questions, then that one. At the end you have I components, then it means that you have to ask n minus I questions. So you want to show that this I is at least n at most bn. So this I is at least bn because you have I numbers which are all powers of 2 and their sum is equal to n. So the way to write up n as the sum of 2 powers s few s many is the binary representation or dyadic form. So that's the proof of the upper bound.
Yeah,
I think
lower
that-
bound is somewhat so.
Yeah, the lower bound goes basically the same way because
Yeah, we have a game and we just
yes,
explain this.
yes, yes. Basically, I told you the adversary strategy as well. So I think that's the exciting thing, and kind of that's what everybody wants to somehow reproduce in the K generalizations, but this nice number never occurs. So none of the generalizations give this. And of course, there are some motivation to study, like the one that Matti said, or there is a paper where there is some quantum theoretical motivation, but
Quantum theoretic motivation.
yes.
Maybe I think it needs motivation in the first place if it's quantum theory.
Well, I don't know.
And are there some probabilistic
Yeah,
nice
there are.
result about? So imagine we have some majority, then
There are some Kral and others have they have some but I do not know some probabilistic they asked in a probabilistic way the queries, I think, or something like this. There are two papers with some probabilistic thing.
If it is possible to do in 5 minutes, can you explain the idea behind your non-adaptive lower bound? And
Sorry?
cube lower bound.
The non-adaptive lower.
Yeah, just the idea, if it's possible. Just
Oh, I cannot. Yeah, so.
With the decrease that I
Hey,
don't
maybe to complicate it
remember
and
the
then-
details.
so but can let's show this. Yeah, this one
This one.
for N3.
I cannot. Can I do it right now?
So it's complicated.
Yeah.
Okay.
I don't think it's complicated. Okay, it is complicated, but it isn't hard. It's just like
So for some reason you need to check all triples.
Yes.
well, basically.
So it's
I
some
think so. So there is some thing that if there is any vertex that appears only in n over 3 or n over 6 or whatever, I don't remember.
So n over a
when there are
constant?
some constant many
So it's something
queries,
like
then you cannot make sure to
Uh-huh.
show a majority more because, or maybe it's a bit more difficult, but not one vertex, but two vertices together, two vertices together, or something like it.
So each vertex should appear n squared times, you say, or
Yeah, but I think it's more like that two vertices should appear together in at least linearly many queries. Otherwise, these two could ruin everything. But I think maybe it's even more complicated than that. But so something.
I also have a question about a similar model, maybe there is something. So suppose you have n balls, but you do not need to know the one with majority color. You just need to know what is the majority color. Is it blue or red?
But, so how do you show a majority
So suppose for simplicity that n is odd.
Yeah.
And there are
Okay.
just two colors.
Okay, and okay.
And the queries are, if you ask three balls, you are told what is the majority color of these three balls.
So you are
Uh-huh.
So
But
you,
you are not shown the ball.
you are not shown the ball, you just know the majority color of three balls, and you can ask, so this is a decision, some sort of decision version. So
Uh-huh.
you are
Yeah, it's a good
told the
model.
color.
I don't know.
Because it would be some computation of in Boolean functions, so
Yes.
connections. Boolean
Yes,
circuits
yes,
and
yes.
so on. If there is some, I think the paper by Epstein and which you mentioned
Hirschfeld?
probably is more related, but we have an adaptive model, and it seems that we have something.
So you think that either the output model or the counting model is just this?
It's closer to,
Mhm.
to yes or no model.
So you want to compute the majority of n variables
Yes, and you are
from the
allowed to-
majority for all triples.
Not all of them, just part.
Just a few.
Just part.
Uh-huh.
So how many majorities you need to know?
Yes.
But can you do anything
So we
better
have-
than take a random set and take a majority of this majority?
It's not clear why this gives you the result, because it's,
Oh, it's some number of.
no.
No, if you take all the majorities of triples and take the
Yes,
majority,
then
it's
it
majority.
will be fine, yes.
But
But if you try to do something random, then it's not clear.
so, but at least is there something better than this? Trying all of them. So imagine you
Yes.
know the majority
Yes.
of
That's
half
the
of the
question.
triples.
Yes, yes, that's
So you have a lot of things. You have triples.
Yeah,
You know
and-
majority for half of the triples somehow. And you-
but not the index, but
Can
you only
compute
know
the
that.
majority of
Yeah.
the entire
You know
thing.
only the color, and you are asked to tell the color.
It's a good question. I don't know whether it's now. I do not know whether it's isomorphic.
It's
To,
it's a different model.
yes.
Just maybe heard something about it because it's
I
interesting.
don't know.
No, actually, I listed all the K set models.
Okay,
What
so
is in the
this is all
literature?
that is known, basically.
Yes,
Okay.
for the K set
I see.
models.
Yeah, actually, so I gave a couple of times talks about this or the other paper I have about this, and always people come up with new models, asking questions, but I think I haven't heard this one. So
Okay, I see.
congratulations for your originality.
Yeah, it's a good model, I think, and
Yeah, I actually thought about this something similar for some time for non-adaptive cases.
so the non-adaptive version you need. Uh-huh.
Because it's basically a Boolean circuit where
Uh-huh.
the majority on the lower end, and then you have arbitrary function on the top, and you need to compute majority.
Uh-huh.
But at least is there a way to avoid at least one triple?
We thought about somewhat different thing. We are allowed subsets of size k, for some k, and on the top also k of, so the function of k inputs. We have, it seems that we have some lower bound.
But not
But
arbitrary
not
function.
very, not very strong, actually, so.
Okay, so basically, thank you for.
Thank you.
Sorry.